Hello, today we are continuing our seminar lessons. So we go over some problems that involve usage of Bayes or law. So for example, if we have here some current, and in the current we have some dl prime region of the current, then at some r distance from that dl prime current, elementary current, we can have some magnetic field created, and if we calculate contributions of all these currents in all the current, so all the wire, for example, in this case, this wire is kind of it's pictured on this picture, and in this case we can have here this integral. So this B magnetic field is total magnetic field that we can have at that point where we have location divided by that R direct R vector, radius vector. Now, if we use this formula to find some magnetic field due to the current wire, that's straight wire here, and the way we need to find out this current, magnetic field of this current, we go over this together. So this, first of all, this dl prime times r vector multiplication is equal to dl prime sine alpha. And in the picture here, this alpha angle is equal to 90 degrees plus theta. We substitute to instead of alpha, and we get this equal to dl prime cos theta. Also, we need to write down expression for dl prime, because we don't have l prime here, and the way we find this is from this triangle here. L prime is equal to s times theta. And from this we find dl prime, and also we need to find out what's 1 over r squared here. So 1 over r squared here, we find out from this, again from this triangle. This s distance that we are given here, we need to express through this s value. So s equal to r cos theta from that triangle again, and from this we have the expression for r squared. So all these values we need now input in the expression for this B magnetic field here, and we have here this dl prime times r, and also this r squared, 1 over r squared. And after we are done with this, we also substitute here this in this expression. Now what we have here is this, after all we are done with, we are left with cos theta in the integral here. And this theta 1 angle, this theta 2 angle are given here from, for example, if we are given here not straight wire, and this theta 1 and theta 2 angles are angles that are formed by the ends of this wire. So we substitute here theta 1 and theta 2, and we have expression for B magnetic field expressed in this value here. So mu naught times E divided by 4 pi s times sine theta 2 minus sine theta 1. So in the case if we have infinite wire, we have theta 1 equals to minus pi divided by 2, and theta 2 equal to pi divided by 2. And we substitute these values, and finally we have expression for magnetic field is equal to B equal to mu naught E divided by 2 pi s. So this magnetic field is just created at some distance s from the straight wire. Now let us have some second example here. So for example, we have here two wires with the parallel directions of the wire of the currents, E1 in first wire, E2 in the second wire, and let's suppose we need to find out here the force per unit length that's acted on the second wire. So in this case we need to find out force by using this ampere force. So ampere force is equal to this expression here, where B magnetic field is a magnetic field due to the first wire that we used before, and it equals to mu naught E1 divided by 2 pi d. So distance now is everywhere is equal to d here, and we substitute here in this expression. So again here dl and B magnetic field, they form 90 degrees angle here, and we just are left with this expression for the force. So suppose this integral dl is the total length of the wire. We divide by this total length of the wire, and in this way we find out the force per unit length that's acted on the second wire, which is equal to this expression here. So mu naught divided by 2 pi, E1, E2 divided by 2. Now let us have some second example here, and this example is this one. So we have here this current that's on circle, and we have current value is equal to E, and we need to find out magnetic field at the distance Z from the center of this circle. So again, we need to use here this Biot-Savart law here, which is equal to this value here. Now here dl times r, dl and r here, this angle equals to 90 degrees. R here, this r is just length, is distance from this dl prime elementary current to the point where we need to find out this magnetic field. This expression for r squared, we find that again from this triangle. So this r squared plus z squared, and we substitute all this to this expression for the magnetic field, and we are left with this value. And here we need to multiply by cos theta, because here, for example, the magnetic field due to dl prime, and that the point is equal to dB, and this dB magnetic field forms theta angle with z axis. And from this we realize that if we find out all the values, all the contributions from all these circle current, we can deduce that only the z contribution is not equal to 0, and all others, x and y, in this case are all equal to 0. So cos theta from this expression again is equal to r divided by r squared, because that's squared in 1 or 2 degree, because this theta angle is equal to this angle, and cos theta of this angle is equal to this adjacent side of this triangle, which is r, and to the hypotenuse, and hypotenuse is equal to this r squared plus this squared and the square root. So we substitute all this to this expression, and we find out that this we need to here integrate on phi, and integral on the phi gives us 2 pi. And finally, we have expression for the magnetic field, which is equal to mu naught E divided by 2 r squared divided by r squared plus z squared in the 3/2 power. So all these were examples on the linear charge distribution. So for example, if you have magnetic, if you need to find out magnetic field due to the surface currents and some volumetric currents, we need to use these expressions. So again, this is the Biot-Savart laws, but this in this case, first one is for surface currents, and second one is for volumetric currents. So for example, if we have here some other cases, for this case is we have here square loop, and on square loop we have current which is equal to I, and the magnetic field we need to find out in the center of this current. So for this case we can use this formula that I used before. Here we have theta 1 and theta 2 angles. So sine theta n, theta 1 and theta 2. So again we can use this here. So for example, suppose we have electric current in that direction. So let's write down 1, 2, 3, 4. So using the right hand rule, we can figure out that this is a current magnetic field at the center due to the current one is directed to us. Same thing we can deduce from this side, from other three sides, so 2, 3, and 4. And each one gives same contribution because they will have same value of theta 1 and theta 2. So for example, if we use here this, now this becomes theta 1, and this is theta 2. So theta 1 is equal to minus p divided by 2 here, and theta 2 is equal to p divided by 4, not 2, or p divided by 2, 45 degrees. So if we substitute to that expression, we have here magnetic field due to the one side is equal to mu naught E divided by 4 pi s, and here multiplied by sine p, well, this becomes 2 sine p divided by 4. So we have here 2, and this finally becomes p1 because sine p over 4 equals square root of 2 divided by 2, so it becomes square root of 2 divided by 2 mu naught I divided by 2 pi s and 2 pi s. So this expression for the only for one side of this. Now if we find out all contributions, so we need to now multiply by 4, so this becomes 4, 2 square root of 2 mu naught I divided by 2 pi s. So this finally is 2 pi, well, this in this case s is equal to, for example, I divided by 2, and here b is equal to 2 square root of 2 mu naught e divided by p I, where I is the side of this square. So this expression we need to use everywhere, and this is useful for solving this problem here. Now let us use here expression for the second problem, and the second problem we have here. Okay, now we can have here this expression for this formula. So we have here again formula. So this is our current. Now from the electrodynamics, we know that magnetic field due to the, if we have current in the form of the circle, magnetic field inside of it will equal to the mu naught I divided by 2r. So this expression for the magnetic field due to the current here in the circle, in the circle contour here. So, and this here is just quarter, 1/4 of this magnetic field, because we have here only this 90 degrees or quarter of this length here. Now, suppose here this length is equal to B and this is equal to A, just like in that problem that we're doing here. Now, magnetic field due to this current on the B radius is equal to here B equals to mu naught E, and here 2B. And BA is equal to mu naught I, 2I, 2A. So B magnetic field resulting is equal to BB minus BA. So this is our result in this case.